we have the honour of having John Schuler. Schuler. I'm terrible at names, including my own, and my wife's name as well, actually. John's a Ph.D. candidate?
Not quite yet, student still.
Student? Oh, God. Yeah, can we kill this instead again? No. Ph.D. student in economics?
Yes.
Thank God for that. And today he's going to be talking on statistical estimation of general equilibrium. And this is for feedback on a conference he's going to be giving down at Duke in mid-March.
Yep.
And so I think Rob said, if there's anything that's not clear here, grill him on it. So,
right. Thank you.
Over to John.
All right, so as is obvious, I'm talking about statistical estimation of a general equilibrium. Now, you'll have to bear with me because I'm going to have to discuss some of the economic concepts to make sure they're intelligible, because I'll be giving this talk primarily to a group of statisticians. So, what is an equilibrium? Well, if you've had at least a principles level econ course, you remember equilibrium as where supply crosses demand. And you have a price that's called the market clearing price, where the quantity supplied equals the quantity demanded. A general equilibrium, in contradistinction to a partial equilibrium, is where all markets at once are in equilibrium simultaneously. Now, before I get into the weeds, why are we interested in this? Well, a few reasons. First of all, equilibrium is the basis of a huge amount of economic theory, but it is terribly, terribly difficult in general to calculate. The computational complexity is exponential with respect to the number of goods in the economy. So in general, it's a non-starter. There are special cases that are easily computable. Secondly, it's a way in to a more general set of questions about complexity science. In some sense, statistics and economics don't meld well together. Statistics is all built around independence, or at least exchangeability. Economics is all built around interdependence. And equilibrium is the ultimate interdependence concept. If someone changes their behavior just a little bit, in general, it alters the equilibrium. Nonetheless, we use statistics and economics all the time, and complexity science is about how we try and reduce apparent complexity and find what complexity is essential. So then, the question as to what extent you can study equilibrium statistically is a special case of a more general set of questions in complexity science. All right, so on to the model. We've got an agent, and they have some endowment. There's a fixed number of goods in the economy. This is an exchange economy only. There's no production. For mathematical simplicity, we're assuming that each good is infinitely divisible. And so the bundles can be represented as elements in the positive orthant of a k-dimensional real vector space, where k is the number of goods. We have a preference ordering that maps that Rk, that should be the positive orthant, onto R. All it is a rank ordering of bundles of goods. I prefer 3 bananas and 2 apples to 2 bananas and 1 apple, so on and so forth. Strictly speaking then, that utility function, since it's cardinal, the utility is actually the equivalence class of these utility functions up to a monotonic transformation. All utility is fundamentally is a rank ordering, but as I'm sure you all know, it is far easier to work in the context of the real number system. Each agent then, given its endowment, which it can trade at certain prices, has a demand curve for every good in the economy. As prices of goods increase, fewer goods are demanded. Those of you who had an econ course remember that demand curves slope down. Okay, So all this means then is the demand curve is a constrained optimization. You pick out the bundle you most want given your budget constraint. Presumably all of us would like to be living on our own island, possibly, but I think none of us here can afford our own island, and hence we aren't living on our own island. Okay. You can then add the demand curve for each agent. You can add those up and get what we call the market demand curve. Okay, so that's demand. So equilibrium. You've got a downward sloping demand curve because as prices go up, we can afford fewer of the goods, hence the slope. Supply curves are upward sloping. That's not terribly important for my present purposes, but the point is this market here with a price and a quantity for a certain good is what we call a partial equilibrium. This is a different partial equilibrium. If you consider these two markets in equilibrium simultaneously, that's an example of a general equilibrium. That's what we're trying to estimate. Now, the dimensions on this grow extremely quickly, so that's a challenge. All right, I hope that suffices as a description of what I'm trying to do. I'm trying to come up with the price vector and the quantity allocation such that quantity supplied equals quantity demanded. That is to say, that market's clear. So this is just a mathematical description of general equilibrium. Notice the one, strictly speaking, the price vector always has one fewer dimension than the quantity vector. That's because prices are relative. If an apple is $2 and a pear is $1, that means, in essence, that the economy gives up 2 pears for every 1 apple. Okay. So, generally, we reckon everything in terms of dollars, but the numeraire good is the good in which you measure all wealth. In principle, you could quote all prices in apples. The price of your car in terms of a certain number of apples. Okay, so that's general equilibrium. I'm going to introduce a way of visualizing this, which is going to guide us through the rest. But first, we need to discuss indifference curves. So, if you take a utility function and you fix a utility level, and you consider all the possible inputs, that is to say, all the possible bundles that give you the same utility level, that forms, in two-dimensional space, what we call an indifference curve. You might call it an indifference surface more generally, but that forms a set in space. These are a handy bit of machinery. They're used exhaustively in the teaching of intermediate micro. What we need from this indifference curve is not just the curve itself, but also the gradient here is called the marginal rate of substitution. And that's going to come in handy. Basically, your marginal rate of substitution is the rate at which you can substitute among goods while your overall amount of utility stays constant. Think about it this way. I'm going through your grocery bag, and I'm taking out some things and putting in other things, but you like all those grocery bags equally. Then, if I'm doing that, I'm moving goods in and out of your grocery bag at your marginal rate of substitution. Okay. Now, this is an alternative characterization of general equilibrium, and this mathematical characterization is going to become important. If we have a general equilibrium, if the marginal rate of substitution of all agents at the final allocation of resources is the same and coincident with the prices. Hence, this gradient, which is the marginal rate of substitution of one agent, and the equilibrium price vector, the inner products are equal to each other and equal to 1. All right. So, this is the visualization that we'll need for the rest of the talk. I'm going to go over this a bit slowly because this, while it only works in the two-agent, two-good space, it's very handy for visualization. So first, we've got two goods in the economy, good 1 and good 2, right? And I can represent the allocation of these two goods between the two agents with a single point in the space. What this endowment here means is agent 1, which is represented by this corner, has this much of good 1 and this much of good 2. Agent 2 has this much of good 2 and this much of good 1. This is the indifference curve. I draw it through the endowment. This is the set of all bundles in this commodity space that keeps the agent equally happy. This is the same indifference curve for the other agent. They're facing different ways because as this agent moves this way, it gets better off. And as this agent moves this way, that agent gets better off. I mean, one way to think about this is two dogs fighting over a bone. What each agent wants to do is push as far into the space as it can. You want to get the maximum amount of stuff, right? Okay, now, here's where this gets involved. The idea conceptually behind a general equilibrium is assume bargaining is costless. If you and I are these two agents and we're bargaining, if we bargain forever, this final equilibrium allocation is where we end up. It's where you get absolutely nothing more out of me than I get out of you. As in, we bargain perfectly, and each of us gets the best deal from the other we possibly can. That means we traded exactly at this equilibrium price. The slope of this line represents the price vector. You've got this amount of good 2 for this amount of good 1. When you give it up at exactly that rate, when trading from the endowment, you end up at the general equilibrium point. So this is critical. This general equilibrium point is not the only point at which both agents are better off. The lens between these two indifference curves in the Edgeworth box is called the core of the economy. All of these points are points that represent gains from trade. Finally, this is called the contract curve. This is the set of all general equilibrium points for all initial allocations. So here's the mathematical detail. The general equilibrium is a function of both the preferences and the initial endowment. It is not an invertible function because more than one endowment with fixed preferences can map to the same general equilibrium point. In fact, any and all endowments along this line will map to that same general equilibrium point. The contract curve, on the other hand, is a function of the utilities alone. It's a function of the agent preferences. Okay. So, again, this visualization only works in the 2x2 case, but it's going to be the basis of the intuition for this technique. All right. So, there are two things we can find, obviously. The end goal, eventually, is to be able to get this general equilibrium point, which is really hard to calculate. But anywhere on this contract curve is n equilibrium point for some set of initial endowments. And it turns out this is much easier to estimate than this. All right. So again, I've got a mathematical description. I think this slide is repeated. Okay, this is just stuff I already said. Walrasian general equilibrium is a function of the utility functions and the initial endowments. The contract curve is a function of preferences only. All right. Now, there's an alternative way to characterize the contract curve. If you fix the utility level of one agent and find the point in that space that maximizes the utility of the other agent, that is a point on the contract curve. So, going back to, so this indifference curve represents a fixed utility level for this one agent. If I ask the blue agent what bundle along the red line does it like the best, it's going to be this point right here. So we can use that fact to estimate the contract curve. Yes, Joe?
John, could you explain to me this graph as if I'm 5 years old? Please?
Yes. Okay. I can re-explain the Edgeworth box.
But really, really simple.
Okay. All right. So.
What's the C curve? Obviously, supply and demand are there, but what's the C curve?
Okay, so those aren't supply and demand. This
okay,
is,
not supply and demand.
This is the Edgeworth box. So first of all, the box is the entire economy, all the goods. So assume there are 10 apples and 10 pears in the economy. Then this is 10 apples long, and this is 10 pears long, and there are two agents. I can represent all allocations among the two agents with a point in this box. If agent 1 has all 10 apples and all 10 pears, we're over here, and agent 2 has nothing.
And agent 2 would be in the bottom left then, 0, 0, correct?
No, agent 1 is in the bottom left, agent 2 is in the top right.
Top right. Okay, that's 10, 10, and 0, 0.
Yes.
That's your...
But the confusing thing about this is the coordinate system is different from the point of view of both agents. So, if agent 2 has 10, 10, then we're down here. And because that means agent 1 has 0, 0.
Okay.
But their endowments have to add up, since there are two agents, to the total number of goods in the economy. Okay. So, this is an endowment point. It's an allocation, it's the initial allocation between the two agents. Now, from there I'd find the indifference curves. This red curve is the set of all bundles that agent 1 likes as much, but not more than, as its endowment. It's the set of apples and pears that keeps agent 1 equally happy. This blue curve is the same thing for agent 2.
So that curve is, let's say my initial endowment is 3 apples and 3 bananas, and I would be perfectly happy with 2 apples and 4 bananas.
Yes.
Then that curve represents all of those possibilities.
Exactly.
Okay.
And you're right about it. It has to move in that direction. You're never going to give up something for nothing, right? If you have fewer apples, you want more bananas. That's why this curve curves out like that. Okay. The area in the middle here is called the core. These are allocations that both agents like better than what they already have. The equilibrium point is where they both do the best possible job they can bargaining. This point here, for instance, is definitely a place where both agents are better off. But implicitly what happened is agent 2 got a better deal. In other words, agent 1 settled for receiving a lower price than agent 2 would have been willing to pay. So, like, if I have perfect information of your willingness to pay for something, and you have perfect information of my willingness to pay, we can only end up here, because neither of us are giving up something for nothing. But This contract curve, then, is the set of all possible equilibrium points for all possible initial endowments. So, hence, it's a function of the agent preferences alone. And that's where it gets its curvature. If I change the agent preferences, the curvature of these indifference curves changes, and the curvature of the contract curve changes. But a better way to think about the contract curve is if I fix agent 1's level of utility and ask what bundle on this red line is agent 2 happiest with, it's going to be where the contract curve hits agent 1's indifference curve. It's going to be on the contract curve. That makes this contract curve somewhat easier to estimate. Is everyone clear on the Edgeworth box before I move on? Okay. So, we can sample from that space of allocations. That's quite straightforward. It's just two independent uniform distributions. And that gives us all these possible allocations that are candidates for general equilibrium. So, I'm jumping ahead, but this is what we end up with. You'll notice this is the Edgeworth box. This is our initial endowment. And we've got the core, which is in dark blue. The gray we throw out of a sample entirely because these are where both agents are worse off than they already are. That would be like you and I going to trade that, you know, I'm trying to buy a car from you and you're trying to buy a musical instrument from me, and we decide, why don't we just use the car to destroy the musical instrument and damage them both? That's when we end up here where we're both worse off. No one would do that. Okay. So the trick then is to consider the utility space and divide it into discrete chunks. Within each of those discrete chunks of agent 1's utility space, we find, of agent 2's utility space, we find the bundle that agent 1 most likes. So this is important, so I'll go through it again. We divide the utility space of all other agents into discrete chunks. Effectively, we are approximately fixing the utility of the other k-1 agents, and we identify the bundle where agent 1 is happiest. That's what this means. What I've done is taken that sampling over the allocation space, and instead of plotting the bundles, I've plotted the utility of agent 1 against agent 2. You'll notice that this forms a natural boundary. That boundary corresponds to the contract curve. So if agent 1 has utility 4, what bundle makes agent 2 happiest? This one. Agent 2 has utility of, that looks like 3. What bundle makes agent 1 happiest? That's here. That edge is the contract curve. So what we're doing as a statistical matter is estimating the edge of the support of an unknown and possibly quite complex probability distribution. But, as we all know, at least I assume we all know, you can estimate the maximum possible value of a probability distribution with the maximum observed value. Mm-hmm. This causes some problems, though. Trying to estimate a parameter that determines the range over which your probability distribution, estimating a parameter that determines what we call the support of your probability distribution, which is to say what you can observe, is an elementary example of something that tends to break a great deal of elementary statistical theory. Our main problem here is this can never be unbiased. A statistic is unbiased when, on average, in the long run, it finds the so-called true underlying value. In other words, the expected value of the statistic is the true value of the parameter. This can basically never be unbiased, because if you're estimating a maximum, you can only be low. You can never be high, because you're never going to observe something higher than the maximum possible value of something. All right, but this is an estimate of the contract curve. Now, let's put that back into the Edgeworth box space. In yellow, these points here become these yellow points here. And as you can see, it's a viable estimate of the contract curve. So, if the contract curve is what you want, if all you need is an equilibrium, not a particular one, then you're basically already done. What you'd want to do to make this better is try and tighten up the dispersion of these yellow points. And then you can use any number of, probably non-parametric curve fitting techniques. I mean, one thing statisticians are very, very good at is curve fitting. The way you narrow that is actually by, when you discretize the utility space, you have to choose how fine to make that discretization. Making it finer will tighten this up. Also, taking more samples will tighten it up. Of course, both of those things get fairly computationally expensive, because recall, I'm doing this in a two-agent space with a grand total of 4 dimensions. But in general, the dimensionality grows both with respect to the number of goods and with respect to the number of agents. Okay, now, this is actually very hard to see. Here in green is the actual Walrasian general equilibrium point. This is a simple case where I can calculate it directly, and I use it to sort of test this method to see if it's tracking correctly. Anyway, so how am I going to take this contract curve and turn it into a general equilibrium? Well, I'm going to make use of the marginal rate of substitution fact I mentioned earlier. I can calculate the cosine between the price vector and the marginal rate of substitution of each agent. If you have the actual equilibrium point, all those cosines should be equal to each other and equal to 1. Now, I have agents, and what I can do is I can calculate the variance of those cosines over all the agents. That's going to grow the further you are from general equilibrium, because not only will the marginal rates of substitution will not only get further, the cosines will not only get further from 1, but they'll also get further from each other. So the reciprocal of that can be used to weight an average. This means that the points closer to this general equilibrium point influence the average more. And of course, hypothetically, if you hit the general equilibrium point head on, then its weighting is infinite. Now, actually, you're just dividing by 0, but obviously you're never going to exactly hit this point. Okay, so how does this work? Well, this is the cosine of agent 1 with the price vector. We want it close, we want it peaked at 1, and it is. We aren't always so close, but it at least seems to be peaked where it should be for now, and that's nice. Now again, remember I pointed out that this can never be unbiased, because I'm estimating a maximum, and sure enough, that's kind of what we see. But the fact that that cosine is close to 1 does indicate that this method does a decent job at estimating the equilibrium price vector. So if your input into your agent-based model is a price vector, then I think this technique may be promising. So far, it doesn't do so well for the actual allocation. So these numbers aren't super meaningful because the scale is arbitrary, but the important takeaway from this is centered not too far from where it should be. Now notice, if the estimator were unbiased, it should be centered exactly at 0. The center on this dimension is close, the center on this dimension is far away. And that's the bias coming in from the fact that we aren't estimating this contract curve precisely, so we're going to be systematically missing things just a little bit. I have not done exploration yet into what amounts of bias are relevant for agent-based modeling applications, and indeed that's quite a general topic. But my initial motivation for this was I needed an equilibrium to sort of bootstrap an agent-based model. In other words, give it an initial equilibrium that it could then change, as opposed to getting it to converge to one right off the bat. But I didn't want to be stuck in the simple cases where you can calculate the equilibrium directly, because those have their own problems. In particular, you'll notice I did all this using real mathematics. We all know that in the context of agent-based modeling, since computers and real numbers do not get along, the fact that all of economics is based on real analysis is kind of a cumbersome problem for agent-based modeling. All this method relies on, though, is a meaningful concept of marginal rate of substitution. Here it's a gradient. It doesn't have to be. Nothing depends on using the infinitesimal calculus here. In any case, we've got something that appears to be converging, but it's biased. So, conclusions. Works okay for the price vector, not so well for the allocation. My suspicion is you can improve both the bias and the computational efficiency by exploring clever ways to sample the allocation space, but I haven't had time to look into it, unfortunately. This is not my only ongoing project. But that's all I have for now. Questions? Oh, yes?
Real numbers and agent-based modeling not mentioning, why take them?
Pardon me?
Why did you choose an agent-based model?
So in my particular context, I work on agent-based macro, and traditional macro has to make simplifying assumptions to make the mathematics tractable, which is fine. But a lot of macro makes what are called representative agent assumptions. It assumes that all agents in the economy are the same. Now, the whole reason we have markets is that all agents in the economy aren't the same. There's a reason I'm doing this and not farming, right? Presumably the people who are farming are better at farming than I am, and hopefully I'm better at doing this. That's what economists call comparative advantage. Agent-based techniques can consume that kind of agent heterogeneity and that kind of complexity. And my suspicion is like representative agent models are a large part of why macro has fallen far short of the hopes placed in it for basically the entire history of the subject. So yeah, that's the answer to the question of why agent-based modeling for this purpose.
You said real numbers or something like that. Agent-based models are not good with real numbers.
Because every number is an estimation.
Yeah, so computers don't do real numbers. That's my only point. And so
it's an estimate of real numbers.
Oh, the estimate of real numbers, not actually using real numbers in a simulation.
See,
right.
They come from a background where mathematicians and economists, real numbers have to be continuous.
Yeah.
The moment you discretize them is the moment it's not real anymore, as far as they're concerned.
Oh.
It's a theoretical distinction.
Oh,
it's
yeah,
not
I'm
really
sorry.
important
Okay.
for us.
Yeah.
It's just theoretical.
Yeah. I'm sorry. I forget that not everyone here is from a mathematical background. Yeah.
I mean, most of us here are not.
Right. Okay. So yeah, but because computers are basically giant adding machines and they don't do continuity well, that causes issues for a lot of economics. Like in particular, the assumption that goods are, infinitely divisible. Obviously, that's not true in real life, but it simplifies the mathematics greatly and doesn't fundamentally change the economics because you can scale things arbitrarily. I mean, your measurement units are arbitrary. But the thing about an agent-based model is while the measurement units are arbitrary, you also have to specify them. And that can be a real headache. Yes?
So where are you presenting this?
Where?
Where?
At a conference at Duke in mid-March.
Is it economists?
No, it's statisticians. That's why I'm like, to economists I wouldn't have explained what an equilibrium was, but I think it sounds like I need to go through that actually more slowly next time.
So, Godin Sunder, what is it, 93? Yeah? 93.
Zero intelligence model.
Zero intelligence one. So what happens, you had two agents in your sims?
Yeah.
Right. So that's an issue. Maybe Andrew can speak better.
No. I was gonna, if you could ask the question I'm thinking of, go for it.
So you've got two agents.
Yep.
The preferences and price factors are allocated. They don't behave differently. Are they homogeneous?
So they have different preferences, but their behavior is pretty simple. So there's no actual agent-based behavior in this, in the sense that I'm basically just sampling over the commodity space and asking the agents how much they like it. I'm evaluating their utility functions there.
This sounds a lot more like a micro simulation.
This for now is, because this is, the point is to estimate this as an input into an agent-based model. It itself is not an agent-based model. Yeah, my motivation was I needed an equilibrium to start an agent-based model I'm building, because otherwise you have to converge to it, and even if you have 10 agents and 7 goods,
Yeah.
it's very hard to converge to an initial price vector because everything's adjusting at the same time. Whereas in the real world, if you start a business, most prices from your perspective are just fixed, right? The way real economies start is evolutionary, but in an agent-based model, you kind of have to have a sort of big bang where you get everything started up at once. Estimating a general equilibrium is in service of that problem. Just starting the model up.
But in an agent-based model, the prices, I'm gonna mess up the language here, so bear with me. The transactions that are executed are below the supply and demand curve, because no one will want to spend $100,000
Right.
to buy an apple.
Yeah.
Right? So only the prices that fit that portion of the supply and demand curves are executed. And so an agent-based model essentially gets rid of this idea of equilibrium that you're really talking about. It minimizes it to an inconsequential concept, right?
That's only kind of true, because
But you need many agents and you need heterogeneity.
right. So basically the way I see it, agent-based models allow us to no longer assume the economy is always in equilibrium. We can start with an equilibrium and disrupt it, because the thing is, the reason general equilibrium is the basis of so much economics is it's an okay first approximation of reality in many cases, certainly not all, and especially not during a crisis.
But is supply and demand ever in equilibrium? Like
Never exactly.
So,
Yeah. So yeah, to Joe's point, they are. I mean, it's more like an upper bound. But from your perspective as a consumer, you generally are facing fixed prices, and those price ratios are relatively fixed. Now, yes, because the real economy is dynamic, the whole thing is never completely in equilibrium. But quite a few submarkets are well approximated by it. The first thing to realize about general equilibrium is this. It's a generalization of partial equilibrium. While the initial motivation behind the development of the concept was thinking of the whole economy, it need not be used that way. And so, if you've got any entrepreneurship going on anywhere at any time, then no, strictly speaking, the entire economy is not in equilibrium. But that doesn't mean an equilibrium model doesn't work well for, say, many commodities markets.
In the short term.
Yeah, in the short term. Obviously, in the long term, the equilibrium shifts. There's an interesting, the interpretation of equilibrium and to what extent the real world is approximated by it is the fault line in a lot of, somewhat frankly politicized economics debates. I mean, I've heard of Chicago economics described as markets work, use markets. Keynesian economics described as markets fail, use governments, and Austrian economics described as markets fail, use markets. And it's all about, what this concept of equilibrium means and to what extent the economy is in equilibrium or not. Yes.
Can you go back to your plot, the red and white? Yes, this one, yeah.
Yeah.
So if you run this over and over again, will the difference between, basically, is the bias always going to be that large?
The bias is always substantial. Remember, this is on an arbitrary scale. I
Right.
just didn't have time to get rid of those numbers.
Right, so is it, I guess, if you know that the bias is 5,000, can you just add or negative 5,000, can you just add 5,000 to...
Well, that's going to be sensitive to the initial conditions.
I see. So this is going to, it's dynamic.
I haven't been able to generate enough data to see if I can find a pattern on which to base a bias correction.
Yeah, that's what I was, okay.
How is that calculated, by the way? How is that just the correct value minus some?
Yeah, it's the theoretical equilibrium minus the estimated equilibrium.
Why don't you just divide it by the variance?
I could do that, yeah.
Because then, well, that would put it into terms where if you scale your data, it wouldn't matter.
Yeah, that's a good idea.
Picture.
Yeah, that's a good idea.
Yeah.
What are the axes?
So this is one commodity, this is the other, and this is how different they are. And this run had very big numbers of commodities in it. But yeah, it's basically, if this were working exactly right, the thing should be centered at the 0, 0 point. But as it is, there's a heavy bias, and it's not. So this is to some extent, notice that when I do this, I have to pick which utility to discretize. My suspicion is if I switched back and forth between discretizing this one and this one, I'd redistribute the bias and possibly even lose some of it, because if we have this little chunk and we're finding the maximum there, then we're falling short up here, and we're always off in a certain direction. If sometimes I'm finding the maximum for this agent in this little space, then I'm not going to be off in that same direction all the time. In other words, one agent isn't always getting gypped out of some of its utility in the allocation. But I haven't gotten a chance to try that yet.
I'm still getting my head around it. If there's multiple agents, which you would expect, like we would think of, like in the economy, we have multiple agents. How would it work in this model? Like in the zero intelligence model, I'm assuming you've seen that in most parts. You would have like this supply and demand curve, and they evolve. Yeah. What would your space look like if you had multiple agents buying and selling or competing for it?
So that's a good point. The thing is, equilibrium abolishes all of that, which is why it's so useful and also so troublesome. When you allow agents to trade at off equilibrium prices, the supply and demand curves actually shift around. And so yeah, in an agent-based setting, equilibrium is where things come to rest. And that is going to be somewhere on this contract curve always is where the system will come to
That's
rest.
if there's two agents, and what happens if there's multiple agents competing for the thing?
Then the contract curve becomes a surface, and the order really does matter there. So if all agents know the equilibrium prices, sellers won't accept less and buyers won't pay more, and the order in which agents trade completely doesn't matter.
Why should they know what equilibrium price is?
Oh, generally they don't. But if you're working in, say, agricultural markets, you basically there's a single market price for wheat, for oil. There are cases where it is reasonable to assume agents have perfect information regarding prices, and cases where it's not at all reasonable to assume they have perfect information of prices. It's a matter of using the model where it helps and not where it misleads. I mean, anything that's traded in an electronic market these days, obviously the prices change, but the equilibrium models work quite well for those, because equilibrium is a zero arbitrage condition, and if you identify an arbitrage opportunity, that's where you buy something at a lower price and sell it to someone else at a higher price, then you are basically moving the market towards equilibrium. In the zero intelligence trading world, that's where an intelligent agent comes in and says, I can get this from you at this price and sell it over here. But once that arbitrage opportunity is undertaken, it's gone, and the market is moving towards equilibrium. And if that if that exchange is observed, then the other agents get price information.
But arbitrage can occur under zero intelligence conditions. I think someone else did that after Bill and Sunder.
Yeah,
I mean, you can emerge all these behaviors with very simple rules.
Yeah,
so I guess the
just
question is, since you're already kind of there at the agent with a halfway agent model, when you take advantage of it and build it out all the way and make it a multi-surface Edgeworth box. I don't think I would want to see that, but
no, yeah, it's
but it'll be interesting.
Yes. So the thing is, yes, you can do all of that, but it takes time to converge on it. So the other thing about the zero intelligence traders is, I should have mentioned this earlier. Rob likes to point out that the median of the trades is roughly the equilibrium price. That's true, but while it's an estimate by virtue of the fact that it takes place in this core, it's not an estimator in the sense that it converges on the actual equilibrium price. The first thing I tried. So, has anyone does it make sense to all of you that you can't naively extend a median into multidimensional spaces, right? Because the real vector space, like Rn, isn't ordered. You can't say that this point is higher than this point. So you can define a multivariate median in statistics using something called the depth function. One of the first things I tried is to calculate the depth function of this core and see if it estimates the equilibrium, and it doesn't. It looks better in the zero intelligence traders model in one dimension, because you're in one dimension and you don't have nearly as many ways to be wrong. But yeah, more generally, there are times when it's appropriate to let the agents converge on their own equilibrium, but in my particular model, I wanted them to start with an equilibrium and then change it. So, they're still agent-based in that sense, but this is an input into an agent-based model, not an agent-based model itself.
Any other questions, John? If not, thank you very much. You'll stay around if
Yep.
we're a little bit longer if there are some questions.
Sure.
So yeah, thank you so much.
Right, thank you. Pardon me?
Oh, your explanations were good. You were
Oh, good.
dumb it down for us now.
No, that's